Welcome back. We're talking about the proximal gradient algorithm. We're interested in minimizing composite functions. I want to minimize a function f of x that's equal to g of x plus h of x, where g of x is smooth and h of x has an easy to evaluate prox operator. And my algorithm that I'm going to use is xt plus 1 is equal to, so what was our usual gradient descent algorithm? Xt plus 1 was equal to xt minus eta times the gradient of f. But f is no longer smooth because it's the sum of g and h. So it's the gradient of g at xt. And all of this, I apply the prox operator of eta times h. And remember that if h of x is equal to the indicator function of a set, then my optimization problem is equivalent to just minimizing g of x subject to x and x, and my proximal gradient algorithm becomes simply projected gradient. Because when h is equal to the indicator function, then the prox operator of h is just the projection operator. So we need to get a few properties of the proximal operator and think about how we proved convergence rates for gradient descent of smooth functions and see what we need for proximal. So one important property of proximal operator is very close to another property of projection. So recall that for projection onto a convex set, and again, when I'm talking about proximal operators, we're only talking about proximal operators of convex functions. So for projection, y1 minus y2 was greater than or equal to the distance between the projection onto a convex set of y1 minus the projection onto the convex set of y2. In other words, projection is a contraction operator when you're projecting onto convex sets. So similarly, prox satisfies something akin to this. And showing this is going to give us good practice for understanding how manipulations with a prox operator work. So the prox operator, x minus the prox of y, is less than or equal to x minus y. In fact, I'm going to show something a little bit more, but it's basically equivalent to this, that the dot product of the prox of x minus the prox of y times x minus y is greater than or equal to the prox of x minus the prox of y squared. So why does one follow from the other? This follows from this follows by Cauchy-Schwarz. Follows from this simply using Cauchy-Schwarz inequality. Okay, so let's see how this inequality, where this inequality comes from. So let's let u equal the proximal operator applied to x. And let's let v equal the proximal operator applied to y. And again, let's write out what the proximal operator is so we can remember. So u is equal to prox h of x means that it's equal to the argument of h of u plus 1/2 x minus u squared, which is equivalent, just by taking the subdifferential, looking at our characterization of an optimal solution, this is equivalent to writing that 0 is an element of the subdifferential of h of u plus u minus x. There's a sign flip there because of chain rule. Or x minus u is an element of the subdifferential of h of u. This is a very simple thing, but we're going to use it again and again when we're talking about prox. It's one of the main defining things. And so we know that this is true, and similarly, we also have that y minus v is an element of the subdifferential of h at v. Okay, so let's see how this, what we can use from here. Now, h is convex by assumption. And in particular, this means that its subdifferential is monotone. So remember what this means. This means that this implies that any element of the subdifferential of h at u, what element am I going to choose? Well, I have one sitting right in front of me. X minus u. So this is an element of the subdifferential of h at u minus any element of the subdifferential of h at v. What element will I choose? The one that's sitting right in front of me, y minus v, times u minus v is greater than or equal to 0. The basic property of, this is the definition of monotone. And if we write out what this is exactly saying that x minus y, u minus v, is greater than or equal to u minus v squared. U minus v dot product with u minus v, I brought that over onto the right-hand side. And this is exactly the inequality we want to write. So just writing out what x, y, u, and v are, this is saying that x minus y times prox h of x minus prox h of y is greater than or equal to prox h of x minus prox h of y squared. And again, just by Cauchy-Schwarz, this implies that prox is a contraction. So this is useful. Most important is just getting used to this manipulation of the proximal operator is defined by an optimization problem. And therefore, if we want to understand it, we need to continuously be looking back at the characterization of optimality. Okay. Now, we want to give a rate of convergence for the general proximal gradient algorithm. And let's think back again to what was the main thing that we needed for smooth functions. So for gradient descent of a smooth function g, the key inequality that we used was that g of xt minus 1 over beta times the gradient of g of xt. This is basically my gradient update when my gradient step is 1 over beta. This is less than or equal to g of xt minus 1 over 2 beta times the norm squared of the gradient of g evaluated at xt. We've used this over and over and over again. Okay, this comes from the quadratic upper bound. But what do we have now? Now I don't even have xt and xt plus 1. Remember, before my algorithm was xt plus 1 was equal to xt minus eta gradient of g of xt, so this was really equal to g of xt plus 1. And if you think about how all of our proofs have gone, they've used the fact that xt plus 1 minus xt is some quantity that we could point to. But now xt plus 1 is a little bit more complicated. Xt plus 1 is equal to the prox eta h of xt minus eta gradient of g of xt. So it's harder for me to say what xt plus 1 minus xt is. It's not exactly the prox, not exactly the gradient, but we need it. So we're just going to define a quantity and define it as the difference between xt plus 1 and xt. So this is called the gradient mapping. I'm going to define g eta of x to equal 1 over eta x minus prox of eta h times x minus eta gradient of g of x. Where did this come from? It comes exactly from wanting to write xt plus 1 as an additive increment of xt. So this gives xt plus 1 is equal to xt minus eta times the gradient mapping. And so at least semantically, we're a little bit closer to what we had when we defined gradient descent, when we just had gradient descent. So we're going to be working with this gradient mapping. And ideally, we'd like to show that it has similar properties to the gradient. But we should note that g eta of xt in general is not in the subdifferential of f of xt. Remember, we're trying to minimize, our overall goal is to minimize f of x equals g of x plus h of x. And what we're saying here is that proximal gradient algorithm exactly translates into this increment of xt plus 1 equals xt minus eta times something. And I'm just pointing out that here this something that we're adding is not the gradient necessarily, not even a subgradient. It might not be even in the subdifferential. So when we look at trajectories, we shouldn't expect that the trajectory of gradient descent of proximal gradient to match the trajectory of a subgradient method that we could equally well use on f of x. Everything inside is convex. G is convex, h is convex, their sum is convex. So I can always run the subgradient method on f of x directly. But we're not going to do that. We're going to run something different. And my point here again is how it's always interesting to note how a particular algorithm deviates from the obvious algorithm, which is just roll downhill. A proximal gradient algorithm is doing something different. So even though it's true that the gradient mapping is not necessarily in the subdifferential of f, it still has a number of very important properties that are very similar to those of a gradient or the subdifferential. And one is that optimal solutions are the only fixed points of the proximal gradient update. Or another way to write this is let's again just write out what that proximal gradient update is. And so the proximal gradient update is xt plus 1 equals xt minus eta times g eta of xt. And the sentence here says that only when we're at an optimal solution will we stay there. In other words, only at an optimal solution, so an equivalent way to write this is that g eta of x equals 0 if and only if x minimizes f of x, which is my composite, g of x plus h of x. So it is also true, if f were smooth, that a gradient of f would be equal to 0 if and only if x were a minimizer. And it is true that x minimizes f of x if and only if 0 is an element of the subdifferential. But g does not necessarily need to be an element of the subdifferential. Okay, so let's see why this is true. So g eta of x hat equals 0. What's this equivalent to? Well, let's write out what g eta is. Now let's remind ourselves what g eta is. So recall, just so I don't have to flip back to the previous slide, I'm just going to write out the definition again. G eta of x is equal to 1 over eta times x minus prox eta h of x minus eta gradient g of x. Okay, so what is g eta of x hat equal to 0? This is exactly like saying, just looking at this definition, that this will only happen when x hat is equal to prox of eta h x hat minus eta gradient g of x hat. And I just said g of x to 0, and I just took the implication of it. Note that I ditched the 1 over eta because I can just multiply through since I'm just setting equal to 0. Okay, so what does this tell me? This is exactly like saying, is exactly equivalent to x hat minus eta gradient of g of x hat minus x hat is in eta times the subdifferential of h of x hat. Where did that come from? This is important. Again, these are simple computations, but there's so much notation that it's important to make sure that we're understanding, we're getting the intuition of the flow here. So there's a lot of intuition, there's a lot of notation here, so just remember what we had derived on the previous slide, that u is equal to prox eta h x. Well, this means that u solves, means that 0 is in the subdifferential of h plus 1 over eta times u minus x. Bringing this over to the left, this was equivalent to writing that x minus u is an element of eta times the subdifferential of h of u. So u is equal to prox of x is equivalent to x minus u being in eta times the subdifferential of h evaluated at u. And this is exactly what I have. So what's playing the role of what here? So x hat is my u, and my x is this entire term. So x comes down here, minus u, that's my x hat, is an element of eta times the subdifferential of u, which is x hat. Okay, so this is a lot of notation, but it's a simple consequence of that. So back to that other color, let's continue down here. So this is just rewriting, noticing that I have x hat minus something minus x hat. The x hats go away. So this is telling me that minus eta times the gradient of g of x hat is an element of eta times the subdifferential of h of x hat. The etas cancel, and bringing over the gradient onto the right-hand side, I get that 0 is an element of the gradient of g of x hat plus the subdifferential of h of x hat. So what is this? What have I just concluded with here? Well, what was our original problem? Our original problem is to minimize g of x plus h of x, and our characterization of optimality says that x hat is an optimal solution exactly when 0 is an element of the gradient of g of x hat plus the subdifferential of h of x hat. So what we've seen is that x hat is an optimal solution of g of x plus h of x exactly when, if and only if, the gradient mapping evaluates to 0 there. So this is another important property that we've got. We need to give a key lemma for proximal gradient, something that's going to replace that key descent lemma that we had. And so we need an analog of g of x minus 1 over beta gradient g of x is less than or equal to g of x minus 1 over 2 beta times g of x squared. And the key lemma that we're going to show is the following. F is equal to g plus h, where g is beta smooth, and alpha strongly convex, but I'm going to allow for alpha to possibly be 0. I'm basically going 2 for 1 here. We're going to derive a lemma that has an alpha in it. So if your function also happens to be strongly convex, then something stronger holds. So alpha may be 0. In other words, my function may just be smooth and not be strongly convex. And I'm going to take a step size eta that is going to typically be 1 over beta, but certainly no more than 1 over beta. Then the key lemma that we're going to need tells me that f, so this is a statement about f, not just of g. F of x minus eta g of x is less than or equal to, note that this is starting out exactly like what we had before just for smoothness, is less than or equal to f of z plus my gradient mapping, g eta of x, times x minus z, minus eta over 2 times g eta of x squared, minus alpha over 2 times x minus z squared. Okay, so why is this key lemma, and why am I saying that it's really the analog of what we need? Let's look at a consequence of this basic inequality. Let's use a lemma with, so I have, this lemma has an x in it and it has a z in it. So I'm going to use z, set z equal to xt, and also set x equal to xt. In other words, z equals x. So plugging in z and x equal to xt, what do I get? This lemma says that f of xt minus eta g of xt, this is also known as f of xt plus 1. Remember, this was our whole definition. The whole reason we defined this complicated thing called the gradient mapping was that I wanted xt plus 1 to just be xt minus eta g of xt. So f of xt plus 1 equals f of xt minus g eta g of xt, and now I'm going to use this lemma, is less than or equal to f of z, z is equal to xt, plus something, but I've got an x minus z, and I'm setting x and z to the same thing, so the second term goes away, minus eta over 2. If I choose eta equal 1 over beta, I would get 1 over 2 beta here. And then my third term, x minus z, again, x is set to z, so this is 0. So you see that this is precisely the analog of that first. So compare it to the inequality at the top. And so this is telling us that we have that proximal gradient descent algorithm is in fact a descent algorithm, and it is strictly improves unless g eta of xt is equal to 0, and we showed on the previous slide that that will only happen at the optimal solution. So proximal gradient descent is a descent algorithm, and we have this inequality that exactly mirrors what we had just for the simpler setting. We're going to stop now, and next time we're going to prove this key lemma. See you next time.